Hello and welcome to another Introduction to Astronomy lecture. This is lecture number 7, and we will be talking about Venus and Mars, our two closest planets in the solar system. So our objectives for today's lecture is we will talk about the visual and compositional characteristics of our two closest planets in the solar system, Venus and Mars. We'll use comparative planetology to compare them to Earth and how they are similar. We will then talk about the very interesting geology of Venus and its runaway greenhouse effect. We will then talk about the geology of Mars and the possible hints for water on Mars in the past. And then we will talk about the runaway refrigerator effect on Mars. Mars and Venus are incredibly interesting worlds for us to talk about because of their similarities to Earth and how they evolved differently. So these are terrestrial planets that are the nearest planets to Earth in the solar system, and that means they are the most accessible for us. So for decades now, we have been able to learn more about Mars and Venus and how these planets diverged in their evolution to be so different that and have their characteristics that they do today and how they're so different from Earth. Venus is pretty close at 0.72 AU, and Mars is a little further out at 1.52 AU. So that means that Venus is actually closer to us than Mars. And that means that they also are both very bright in our sky. Venus was sometimes called the evening or the morning star because it could always be seen in the evening or morning, since it is in the interior of the solar system, since it's closer to the sun than us, we could really only see it in the evening and the morning. And it was so bright that it could be easily observed with the unaided eye. And this is partially due to Venus's very thick atmosphere reflecting nearly 70% of the incoming light. That makes it very bright in our sky. Mars, however, appears very distinctly red when we look at it in the night sky, and this is due to the presence of iron oxides in its soil. We can think of Mars as being a little rusty. Another feature of Mars is that it has bright polar ice caps, which are uh, sometimes, it says easy to observe, but I had to use a very large telescope to see these ice caps, and it had to be the right season on Mars to see them. So they are located at the poles, and they are pretty easy to distinguish since a lot of Mars's surface is bright red, and there are some areas on Mars' surface that are a little duskier in surface color. So the poles really stick out when you have a telescope that can see them. And there used to be varying amounts of substructures on the surface, these dusty areas, the darker dust. And when astronomers first looked at them with their cruddy early telescopes, they thought that these could possibly be canals. And this we now know that a lot of this is due to optical illusions and the tendency for the human mind to see random features when we're looking at stuff at the very edges of the optical resolution. So it turns out that actually Clyde Tombaugh, the person who discovered Pluto, when he was looking at Mars, he had it magnified so much that he was actually seeing the shadows of the blood vessels in his eye being projected onto the surface of the lens that he was looking at. So it was absolutely an optical illusion. There were no canals on the surface of Mars, but this idea that there was life on Mars stuck around in our collective imaginations and science fiction for quite some time. Hence the idea of Martians. Mars rotates very similarly to Earth in that it rotates about its axis in 24 hours, 37 minutes, and 23 seconds, which is very close to 1 day's length on Earth. And Mars's axis is inclined at an angle of about 25 degrees. These measurements are almost more than 200 years old and gave a very accurate number. This is because we could see the surface of Mars rather clearly. And also, since Mars is very far away from, or much further away from the sun than Earth, a Martian year is nearly 2 Earth years. Venus, on the other hand, is a lot harder to measure its axial rotation, and that's because it has that dense atmosphere, so you couldn't really tell how much of the surface was rotating underneath. And so to do that, they actually had to use radar. So dating as far back as the 1960s, we know that Venus's axial rotation period is 243 Earth days. So a day on Venus is 243 Earth days. That is a very, very long day. In addition to that, Venus's one Venusian year, one revolution around the sun for Venus is about 117 Earth days, which means that a day on Venus is longer than its year. That's pretty weird. Another weird thing about Venus is that it actually rotates about its axis in a retrograde direction, meaning that it's almost as if something impacted Venus in the past and flipped it so that it was now spinning in the opposite direction. It's a hint that something very crazy could have happened in the early solar system and caused Venus to be rotating the way it is. So now we're going to put on our comparative planetology hats and we're going to look at these planets. So Venus and Earth have very similar compositions, and that leads them to having very similar densities, while Mars has a density much lower that is similar to that of the Moon. And since Mars is approximately half the diameter of both Venus and Earth, while being much less massive, this means that the surface gravity on Mars is 1/3 of that on Earth and Venus. Another interesting characteristic of these planets are their atmospheres. Mars has a very light atmosphere that is less than a percentage of the atmospheric mass of Earth, while Venus has an atmosphere that's nearly 90 times more massive than Earth's. These atmospheres have played a very important role in shaping how they evolved in different ways from Earth. So, unlike Earth, Venus has not experienced plate tectonics. Since 1962, we've launched nearly 50 spacecraft to study Venus. But since Venus has such a very intense and inhospitable environment, only about half were successful, and the longest device that ever landed on the surface only lasted 23 minutes before it melted into slag. So, due to the very high levels of CO2 in the Venusian atmosphere, the only viable methods for really studying the surface is using radar because that thick atmosphere means that we can't look directly down there, and also the surface temperatures mean that we can't really land rovers down there either. So we've got to have things that orbit and use radar to map out the surface. The first global radar map of Venus was made by the US Pioneer orbiter in the late 70s. But the most successful geological mapping of Venus came from the US Magellan spacecraft, which used radar imaging to produce a radar map of the surface that has resolutions down to 100 meters. So this gives us a very rich map of the Venusian surface and is an excellent way to study Venus without having to land down there and experience hell itself. So let's explore the surface of Venus safely using radar imaging. So these radar images have shown a surface that looks a lot like how Earth would have historically before we got all this pesky life on our surface and we were just experiencing volcanism and geology. So, since there are no volatiles and there's such a thick atmosphere on Earth, the weather on Venus is very hot and very dry with some calm winds. There's no natural convection reshaping the surface or geological features, so there's no plate tectonics constantly reshaping the surface of Venus. Overall, the surface is very inhospitable with very high surface pressures thanks to the thick atmosphere, with surface pressures 90 times that of Earth's, and the temperatures are so hot that you can melt lead and zinc on the surface. Nearly 95% of the surface of Venus are lowland lava plains, which forms just like the lunar maria via widespread lava eruptions. And above these lowland lava plains are two continental mountainous terrains. The largest is Aphrodite, and the smaller of the two is Ishtar. Ishtar contains higher peaks and is in the northern highland region, while Aphrodite stretches along the equatorial region for nearly one-third of the planet. Determining the age of Venus is very similar to that of determining the age of Mercury and the Moon, and so the relative age of Venus's lowland plains is best determined by counting the craters. But since Venus has a very thick atmosphere shielding the surface from smaller impacts, very few craters are down on the surface because only the larger impacts could actually make it to the surface. So, to study the age using these methods, the craters are counted in distinct regions and only considered when they are above a certain size, approximately 30 kilometers in diameter. And throughout the lava plains, it was determined that the surface is approximately 300 to 600 million years old, which indicates that's when Venus stopped having persistent geologic activity. So, due to the low levels of erosion on the surface, it's assumed that Venus experienced a mysterious planet-wide volcanic convulsion event during this time, which reshaped the plains entirely, and very little has happened since then. So Venus had a very large burst of geologic activity approximately 300 to 600 million years ago and then stopped. We've been talking a lot about how Venus's surface conditions are due largely to its atmosphere. So let's talk about that atmosphere now. So it's a very thick atmosphere, and these dense clouds block out most radiation and insulate the surface. The most abundant gas in Venus's atmosphere is carbon dioxide, which comprises nearly 96% of the atmosphere. This results in a lot of insulation and gives Venus a greenhouse effect, which means Venus's surface is perpetually hot and dry, and that means that the surface reaches temperatures of nearly 800 degrees Fahrenheit. Understanding Venus's atmosphere and its evolution has very severe implications for understanding our own atmosphere. So if we consider that both planets originally had similar atmospheres and temperatures, this could mean that life on Earth and the temperatures on Earth that we experience could actually diverge at some point, similar to how Venus has diverged and became a experienced a runaway greenhouse effect. So a runaway greenhouse effect refers to perpetual heating of Venus's surface over time, which evaporated the liquid water necessary for carbon dioxide absorption in the atmosphere. And then the ultraviolet light from the sunlight then strips the hydrogen away, leaving Venus to accumulate even more CO2 with no ways to absorb it. And scientists fear that this effect on Venus's atmosphere is irreversible. And if Earth approaches a point of having increased CO2, we could begin our own runaway greenhouse effect, which we would have no potential way to fix. So it's very important that we reduce the amount of carbon dioxide in our atmosphere as much as possible, at least to natural levels. We don't want to have unnatural human activity greatly changing our atmosphere. So now let's go explore Mars, the other planet in today's lecture. So Mars, unlike Venus, is very cold on its surface, but it is also very dry. So the first Martian spacecraft missions began in 1965, but a lot of our really good understanding of Mars began in the 70s with the expensive Viking 1 and 2 landers. And for nearly Nearly 2 decades later, though, NASA began exploring smaller and less expensive crafts, and so now we have a multitude of rovers that have explored the surface. The Pathfinder mission began in July 1977 and was soon followed by Mars Odyssey and Express, and then there was Spirit and Opportunity, and now Phoenix. And they have notably found subsurface hydrogen, which is presumably from frozen water, and later has been directly measuring water in the northern soil starting in 2008. In 2011, NASA launched the Curiosity rover with lofty goals of investigating the Martian climate and geology to assess the potential habitability over time. But Curiosity has no plans for a return mission to bring the samples back to Earth for laboratory analysis, so all of Curiosity's analysis is being done by the rover itself on the Martian surface. However, it should be noted that while there hasn't been a return mission made from the Martian surface material has been studied on Earth via meteorite landings. So it is actually possible that if there is a large enough collision on Mars, some of the material ejected out into space doesn't go back into an orbit around Mars and then fall in. Some of it actually is left behind in the solar system, and eventually the gravitational influence pulls it into Earth and it lands on our surface as a meteorite. And so there are actually a few samples of Martian meteorites that landed on Earth in laboratories around the world. They are incredibly rare and very valuable. So, two of the coolest Mars rovers are Perseverance and Ingenuity. Perseverance was the rover, and Ingenuity was a tiny helicopter. So, in 2021 is when they landed on Mars. And this rover mission was designed to study the Martian surface and search for past signs of life, and to survey the atmospheric conditions and also assess the potential for terraforming, and hopefully bring back material for laboratory analysis. The Ingenuity helicopter also was the first flight on another planet's surface, and it's continued its mission since April 19th, 2021. You can find continuous data from these missions on NASA's website. Earlier in this lecture, when we talked about the comparative planetology of the planets, we said that Mars was relatively small, with having a diameter about half that of Earth and Venus, and it also has a lower density, which suggests that Mars is composed primarily of silicates. And so, although there's no current magnetic field around Mars, there are areas of surface magnetization that suggest that at one point in the past, Mars did have a magnetic field. Mars has highland areas and volcanic plains, and approximately half the planet is covered in heavily cratered highlands, and the other half is younger, lightly cratered plains, which are due to volcanic activity in the past. Interestingly, and unlike Venus, many of the Martian volcanoes appear to be far older and are presumed to be dead due to their observations of heavy crater impacts along the base. If these volcanoes were active, the craters would have been filled over by lava much more recently. So these older craters are signs that these volcanoes haven't been active for a while. There's also the largest volcano in the solar system, Olympus Mons, which has very few impact craters, which means it could be relatively intermittently active today. Although there are no plate tectonics on Mars, there are regions of the surface that indicate tectonic forces took place under the crust, which pushed and bulged the surface. So, unique to Mars and Earth, these tectonic cracks on Mars were shaped by water into canyons, and these undercut cliffs and valleys. So today's Martian landscape includes many sharply defined igneous and some sedimentary rocks. dunes, and deposits of fine-grained reddish soil, which contains clays and those iron oxides, which give it that lovely, distinct red color. Also, unlike Venus, the occasionally aggressive winds on Mars play an important role in redistributing the surface material and causing a lot of erosion. This surface material plays an insulating role to the temperature conditions on Mars since there is very little atmospheric insulation. So that dust in the wind is some of the only ways that there is insulation for the Martian surface. So the average temperature of the Martian surface is minus 81 degrees Fahrenheit. Very, very cold. So now we're going to talk about something really exciting, the possibility of water on Mars. So, since Mars has a more hospitable environment than Venus, it is a promising place to look for life in our solar system. And what we think is the most important thing required for life is water. So, we really need to look for water on Mars to assess if there was potentially life in the past there, or if there's even life there now. So Mars's atmosphere is incredibly thin, being 0.007% of the Earth's atmosphere, and is composed primarily of carbon dioxide, nitrogen, and argon. And so, although there is small amounts of water vapor and occasionally clouds of ice do exist in the atmosphere, liquid water is not stable on the surface in these conditions. Although salt water might be possible to exist in a liquid form in some places on the planet. The bright polar caps on Mars change size based on the seasons. So these seasonal caps are not composed of frozen water ice, but instead are composed of frozen CO2, what we call dry ice, and are only in the permanent or the residual caps underneath the seasonal caps does the frozen CO2 exist with abundant water ice. So only in the permanent residual caps underneath the seasonal caps is there water ice on the poles of Mars. So what we see when we look at the poles changing is primarily the dry ice that is what we see on the surface. These northern permanent caps never shrink, and these permanent northern caps never shrink, and those are what we believe are composed of the water ice. So that part that we see that never shrinks, that is potentially where we have water ice. And so evidence for this water ice was uncovered by the Phoenix spacecraft under a thin layer of dust. And there's other evidence for water in the past on Mars found throughout its structures due to the carvings of the surface. The way that the surface is shaped is very likely due to water flowing over and carving it in the past. So now we can talk about how the climate changed on Mars. For liquid bodies of water to have once existed on the surface of Mars, Mars once would have had to have been a lot warmer and had a much more substantial atmosphere than it does today. So it is assumed among astronomers that, like Earth and Venus, Mars once had much higher surface temperatures as a result of a greenhouse effect. However, Mars's smaller gravity implies that it would be easier for atmospheric gases to escape over time. Also, Mars no longer having a magnetic field means that it's very easy for the solar wind to begin stripping away at that atmosphere. So Mars eventually, divergent of Venus, experienced the opposite, a runaway refrigerator effect, as atmospheric gas escaped and insulation left the planet, meaning this gave Mars a very cold and dry surface that we see today. So climate cycles such as this are expected for any major changes in Mars's orbit or axial tilt, which could cause the polar ice caps to melt and release large amounts of water vapor into the atmosphere. It's been suggested by scientists that you could make a terraforming process this way on Mars to create a more hospitable atmosphere and climate for humans on the surface by melting the poles and releasing a lot of the ices into the atmosphere as gas. So the ultimate question, is there life on Mars, or was there life on Mars? It's been suggested that due to the possibility of water on the surface in the past, that Mars may have once been home to life, or even could presently still be the home to some sort of life. Experiments on Mars done by the rovers have looked for evidence of respiration or absorption of nutrients or various exchanges of gases between the soil and the environment to discern if life was or is present in the soil of Mars. Some of these tests have gone so far as to pulverize and analyze the soil to determine if there is any organic material present. All of these experiments are very sensitive, and it's presumed that they would have easily been able to detect the presence of life should it be there. And so, despite some promising results so far, no conclusive signs of life have been found on Mars. And although no life has currently been detected, there's no reason to believe that life could not have once been present on Mars nearly 4 billion years ago. And so perhaps we just need more samples, more time. And so we hope that the Perseverance rover will be able to unravel this mystery by either finding some fossil records or finding organic compounds in the samples it has collected. This brings us to the end of our lecture on Venus and Mars.